quiz. I don't follow.
It's still material. It's all in mode.
Yeah, it's always moved, and then switch back to it.
Already? You can do a lot of the problems by now.
Switch back.
Just divide everything. So did we do divide everything by
Yeah. Oh, I
do
should
the
say
ratio, and then
by
divide.
tomorrow, yes. By tomorrow. Yeah. We got to get into some titration curves. But I mean, you really have. We're just going to be applying what we're doing now to titration curves. It's going to be a different context. But yeah, I think so. I had a girl come in and she had done more than half of the problems already last night, the first day. Wow. She had to read ahead a little bit to know some of the things that we're doing today. It was great. Okay, so are we still working or are we getting 3.18, 3.17? The stoichiometry step is right here. Now, as I mentioned to Cam a few seconds ago, the worst thing about this when we're at the beginning of the chapter is I don't know what reaction, what equations are right. Once I do that, I'm fine. And so just know that when you add strong acid or strong base, whatever is in the buffer that can neutralize it does that in the stoichiometry step. Single direction arrow, do the moles, find the limiting reagent, and see what the new moles are. Yeah.
Is it always added to a strong acid?
Yes, when we disrupt a buffer, it's always going to be with a strong. If I added weaks, or I had you add weaks, the calculations would be dreadful. It would be horrible. So we're not doing that.
And would the change be a lot more meaningful?
Yes. Yes, it would be. Yep. I don't know if we can pick this up. I don't know if we're filming through Jennifer's head, but I came up with this for my equilibrium reaction. This is not the only correct equilibrium reaction, though. You could have still used, because we were kind of dominated by the action of the NO2 here, you could have used this, NO2 plus water, and treat it as a base, makes HNO2 plus hydroxide. You'd have to use the Kb for NO2. Anybody do this? Did you, Elizabeth, use Kb? Change it over to Kb? You did?
Yeah.
Okay, and yeah, so you'll get the same. You'll have to get the POH and then change it over to pH. You still get 3 point. Right? Good. So once you get to the equilibrium step, either use the acid component and use its Ka, or use the base component in water and use its Kb, and either way you'll get the right pH if you do it right. So we get a pH. Now, this is going to go to the right. That's going to be 2.5 minus x. That's x, and that's 1.5 plus x. And you get a 3.18 or so. I have good news. Real good news.
That's good.
You ready for some good news?
You're ready for tomorrow.
There is a... That's news. I'll give you that. There is a much easier way to do these problems. I wanted you to appreciate how we do them with the stoichiometry step and then the equilibrium step. But there is a far easier way to do this, only using the stoichiometry step and then taking the answers here and plugging them into a simple formula. Can I derive the formula for you?
Derive?
Yeah, we can start doing
You'd rather I just gave it to you. That ain't happening.
No, I like it this way.
It'd be moles divided by liters.
Here we go. Even if you're not interested, I'm going to show you anyway. Don't write anything down. Just watch. This is an acid dissociating. Yes? Is it a weak acid or a strong acid?
We can't tell.
All of them.
Yes, you can't tell.
Equilibrium.
Equilibrium tells us it's weak. That's right.
I mean, even HCl has a bit of HCl.
This is like
Marginal.
Tayshaun Prince when a foul is called on him. Equilibrium signs and weak acid. Stop. Now, that means that if it's weak, we can determine a Ka for it. The Ka is going to be H plus times A minus over HA. Are you with me on that? Products over reactants for an equilibrium. Yeah? I'm going to take this Ka expression and solve it for H plus. Just get H plus by itself. That means we're going to have to multiply out the HA, so it's going to be Ka times HA. So it's Ka times concentration of HA over over, got to divide out the A minus. Do we agree so far? Just manipulating things with algebra. All right. I'm going to just change some little tiny thing about this. Rather than having Ka and Ha both in the numerator, I'm going to pull the Ka down so it looks like this. Ka times Ha over A minus. Is this the same as that?
Yeah.
The same thing. The Ka is still being multiplied by the Ha before the A minus is divided, so it's fine. You're looking like, okay, you're not impressing me yet. But it's good at the end. If this is equal to this, is it true then that the log of that equals the log of that?
Yeah.
Is it also true that the negative log of that equals the negative log of that? Yeah, if two things are equal to each other, that means the logs are the same too. So that's what I'm going to do. I'm going to take the negative log of the left, negative log of H plus. Oh, that looks familiar. And then over here, I'm going to take the negative log of this. So we have another name for this thing, negative log of hydrogen. This is pH. So this thing right here, we're going to call that the pH. Over here, I have just a little bit more algebra to do. If I have the log of two things being multiplied together, can I just say negative log of this plus negative log of that? Yeah, when they're multiplied together, sure. You can expand it. So it's negative log of Ka plus negative log of Ha over A. All right. Now let's give negative log of Ka a new name too. Negative log of H was called pH. What do you want to call negative log of Ka?
PK.
pKa. The pKa of it. Negative log of the Ka, which is a small number, will be the pKa. The lower the pKa, the stronger the acid. Because it's 10 to a smaller negative number, right? It's Ka value, that means it's a stronger acid.
So the lower the PK or
The lower the pKa, the stronger the acid. So this thing right here, pKa is what we're going to call it. Now for this last term, I'm not going to rename this, but I am going to manipulate it a little tiny bit. I have negative log of this ratio. If I take that negative sign away, if I want to make it a positive log rather than negative log, I have to take that negative sign and raise it to the power of that term right there. What happens to a ratio when you raise it to the negative 1 power? It flips. Yeah? So this part right here is going to be positive log. This is going to be hard to read, I know. Positive log of the other way around. Now remember what A minus is. That's the conjugate base, right? So I'm going to call it base. I got that flipped over. Now HA is going to be on the bottom, and that's the acid. We have three terms now, the left and then these two terms on the right. All that's going to be joined together into this equation. This is a thing of beauty, so don't let your mind wander. pH, that's the left, equals pKa, that's the first term, plus log of the base over the acid. This equation, informally, I'm going to call it, and this is what I'll always call it. I just call it the buffer equation. The Zumdals, they're not informal, you know that. The official name of this is the Henderson-Hasselbalch equation.
Buffer.
You can say that if you want to, I'll call it the buffer equation.
What's it called again?
What is Henderson?
Henderson-Hasselbalch.
Did they actually derive the equation?
Yeah, they derived it.
Again,
Yeah.
stating the obvious. Again,
Right.
Yeah.
this equation makes our work way easier. Let's go back to this problem that we did where it was our original messing with the buffer solution. We had 0.1 moles of a hydroxide added. We had to do the stoichiometry. That part you can't get out of. You've got to do the stoichiometry part. And I'll tell you that this ratio, or the log of the base over acid, that is really concentration. However, the ratio of concentrations, if those two things are in the same solution, since their volumes are the same, this is the same as the ratio of moles. This is just a mole ratio of the base to the acid. So this is something that you should write down too. This thing right here is the same as the mole ratio.
Because they have the same volume, right?
Because they have the same volume, the concentration ratio would be the same as the mole ratio. This is really nice because look at this equation. We already have the moles of the acid and its conjugate base. So that last part is taken care of. Let's do this right here. I know that we already did this problem. We did it with the equilibrium part. But we can make a shortcut using the buffer equation. pH equals, what would be the pKa of this acid? Here's the Ka of it, take negative log of it. 3.40. Plus log of the base, which is 2.1 moles, over the acid, which is 1.9 moles. Crank that out with your calculator, what do you get?
3.4.
You get that. So this equation totally eliminates the need to do all this equilibrium stuff. And it takes away a lot of your stress because this is the worst part, is knowing what chemical equation to write. It's all wrapped up into that buffer equation.
Did you ever ask us on a test to do both ways?
Yep. So that's equal to 3.44. I've talked to you before about my feeble memory and my airheadedness. And the fact, when I'm using, and this is the 100% truth, as I have used this thing, okay, then my mind starts to play tricks on me. Is it base over acid or is it acid over base? I can't remember now. So this is the way I remember. Bah! It makes the work so easy. So when I recite this equation, I say pH equals pKa plus log of bah. B over A. Bah.
That's a bah.
Yeah. So I've always just remembered bah. This equation makes it so easy, and I can remember it.
It even says Hasselbalch.
Yeah, yeah, they helped us with
You
it.
guys are so late. Keep that program.
As you get doing the homework, and as the Zoom dolls ask you, okay, you have this buffer and this much hydroxide or hydrogen is added to it, you'll have to do this step. Remember, you can't get out of doing this step because the amounts of acid and base are going to get disrupted. But then you plug in that ratio, and away we go. It gets you the answer real fast. It's nice. Just before we go, I will mention the reading quiz tomorrow. Remember that is a couple of things about it. It's going to involve a titration of a strong acid with a strong base. You need to find the pH at several steps along the way. It's tedious, but it's all stoichiometry. It's all about, okay, which one is the limiting reagent? Going from molarity to moles, if you know the volume. So don't think that, oh my gosh, I just can't understand this. It's stoichiometry. It's just solution stoichiometry. And one of the things that the Zoom dolls do that I don't do just out of preference, and it's annoying to me, because you're going to use a small number of moles, they wind up changing everything into millimoles. So that gets annoying to me. I mean, when they take millimoles divided by milliliters, it gets you to molarity because both of those are cut by 1,000, so the ratio is still the molarity. But I don't know. I'd just rather keep everything in moles and liters just because my brain is small. But just know that it is going to be there, and so don't be surprised. Like, millimoles, what are they talking about? Well, they'll tell you that millimole just means 1,000th of a mole. And so the numbers are a little more convenient that way. Millimoles. And I'll warn you, the solution guide in this chapter is all about millimoles too. So you'll see that a ton.
Well, does the solution guide make sense?
Thanks for that.
What makes sense?
Yeah.
The other stuff is good.
Okay.
嘿。